Welcome back. Today we'll be going over Module 2, Domain, Intent, Entity, and Role Hierarchy. Let's get started. So first, let's talk about query representation. We'll talk about a technique called bag of words. So natural language queries must be converted into a form that can be understood by machines. And there are two common ways to do this, bag of words and word vectors. To represent queries as a bag of words, we must find the unique set of words in the corpus or the vocabulary. So let's say you have an entire news article or blog post. You can take the set of all of the words that are listed in your text, and whatever the set is, we will call it your vocabulary set or V. Right? So you can see here this top row would be V. Now each position in the vector V represents a unique word in the vocabulary. And so when we're given a new query, what we can do is essentially just keep score in terms of how many times did each word appear in the given query and increase that particular index in our vector V by that count. For example, we have the red dog. So we give a 1 for each of the words that show up from the unique vocabulary. Same thing here, cat eats dog, so we add 1 to dog, cat, and eats. And in this example, the highest count is 1, but you could have a case in a query where, let's say, dog was mentioned twice, in which case it would get a score of 2. But in essence, now we have a fixed representation of a given query in terms of a set of words. So this will be helpful for downstream tasks such as classification, maybe even clustering. Now let's go ahead and talk about the second way in which you could represent queries, and that is with word vectors. Word vectors are a latent representation of words, also known as word embeddings. Creating those embeddings can either use two different algorithms, skipgram or continuous bag of words. A shallow encoder-decoder model predicts the neighboring words of a given word. So what we mean here is, given a sentence, let's say the dog jumped over the cat, we can take the word dog as the input, and then the neighboring words would be the and jumped. That's if our window is 1. If we use a larger window, we can capture more words that are near the word dog. And the assumption here is that words that are similar appear in similar contexts. So what this model does is it looks to predict, given an input word, what would likely be its neighbors. And as it does this, it updates two weight matrices. The first is n by v, where v is the size of our vocabulary, so we take the unique set just as we did before, and n is the dimensionality of this hidden vector. This hidden vector is just kind of used as a pass-through state for us to do the compression and then decompression, or encoding and then decoding of this data. Now what happens is we then use one of these matrices as the embeddings for each of the given words, and we call this a word vector. Now after the model trains on this in an unsupervised manner, because it's just scanning through text and getting all these pairs of, okay, this is the word, here are the neighboring words. Let's learn the relationship between all these words. What we end up with is a matrix that is like V by N, and it contains latent representations for each word that we can then use for downstream tasks. Let's take a look at query representation and some visualizations.